Thanks for the introduction. Gen AI, that's going to be a tough act to follow up. Quickly, before we get started, I just want to add that we're going to go through a couple examples. And if you want to follow along with those examples, there's a couple notebooks that you can get on the repo, and you can find those just by scanning this QR code here. So quickly, we're going to go through, for the agenda, what we're going to cover is very briefly and non-comprehensively what the potential outcomes framework is. Then we'll go through a couple motivating examples of how you can use CausalELM within this potential outcomes framework to estimate causal effects. And we'll tie those examples into this general workflow that you can use CausalELM for. And then we'll finally get into the mystery of what the ELM stands for in CausalELM. We'll quickly talk about, besides what we went over in the examples, the other estimators that you can use within CausalELM. And we'll compare it a little bit to some other packages, especially Python packages, and just talk a little bit about the overall design philosophy of CausalELM. And then I'll talk about what I see potentially as the way forward, a little bit with CausalELM, but more generally with causal machine learning in Julia. So briefly, this is going to be the potential outcomes framework. So some of you may have been in the really interesting talks yesterday or throughout the week on causal inference based on structural causal models. I think Sefer had a talk on that, which was really great. And that's to say that this potential outcomes framework is not that at all. So I just want to clear up any confusion and just say that potential outcomes, not structural causal models, and this is not better than structural causal models. It's not worse. I think there's great use cases for both, but this is just a different way to think about causal inference. And so under the potential outcomes framework, you'd usually be given a data set. So you'd have some covariates X, some treatment statuses we'll call T, and some outcomes Y. And so for each unit I, which can be a person or maybe a town or a village, as we'll see in one of the examples later, we'll define xi as a vector of covariates for each unit I, and Ti will take a 0 or 1 as a treatment indicator, and just to keep things simple, but actually it can be categorical or even continuous, and some of the estimators here in CausalELM actually do allow you to use categorical or continuous treatments. And so when unit I is treated, for now we'll say Ti is equal to 1, and when unit I is not treated, we'll say Ti is equal to 0. And then this means, so our outcome is going to be a function of the treatment. That's why we want to estimate the causal effect here of our treatment. And so we'll say when when unit I is treated, then Yi, Ti, we observe Y1, and when unit I is not treated, we observe Y0. And these outcomes, Y1 and Y0, are what we call the potential outcomes, hence the name potential outcomes framework. And so pretty simply, we can see the impact of treatment for unit I is just this tau I. It's Yi1 minus Yi0. So in theory, that's pretty simple, but we have a really big problem, which is usually called the fundamental problem of causal inference, which is we only observe Yi1 or Y0, but not both potential outcomes. So like if you were doing a study, say a randomized control trial, you wanted to see the effect of some medication on some disease, and you had a unit assigned to a group that actually gets the medication, but not the placebo group. Well, you can't see like what that, or the problem you have to solve is that you can't see what the outcome would have been for that person had they been assigned to the placebo group, because you can't be in the placebo group and the treatment group at the same time. And so basically most models that are working under the potential outcomes framework either use some simplifying assumptions or leverage some knowledge about the structure of the data set, or use some clever research designs to try to overcome this problem. And so one example here that policymakers might be interested in is learning the effect of 401k plans on people's net worth. And in case you don't know, 401k plan is a sort of pension plan in the US. It's a private pension plan that employees and their employers both invest in. And once the employee retires, then they can withdraw money from this pension fund and use it to live off of. And so it would be very interesting for policymakers to know whether this actually works or not and how they should or shouldn't regulate it. And so here we want to estimate the expectation of tau I, or the expectation of yi1 minus yi0, which is usually referred to as the ATE, or average treatment effect. And this was actually done a while ago in a study in 1994, the year I was born, by Poterva et al. And so in this study, we have xi, and it includes a bunch of characteristics about the individual employee. You can read those there. In this case, TI denotes eligibility for a 401k plan. So in TI is 1, the individual is eligible to receive a 401k pension, and 0, the person was not eligible. And then YI here represents the net financial assets in US dollars, 1994 US dollars. And so typically the way you could go about doing this, and I think how it was done in the original paper, is you could just use a linear regression, assuming you have randomization, or at least conditional randomization. But an issue there with linear regression is if you have, and especially when you have more covariates, if you don't know the functional form between the covariates and the outcome or the treatment, then you can get a biased estimate. And usually in like econometrics course, you'll hear, well, we can use prior knowledge or domain knowledge, but in reality, we usually don't have domain knowledge of whether we should use like the square root, or the log of some variable. But more recently, there's been this approach called double machine learning by Chernozhukov et al., where we actually don't need to specify a functional form. So we can use any machine learning models to estimate the treatment and the outcomes out of fold and get residuals, and then combine those residuals into a final linear model. And yeah, we don't need to know the functional form, and it works well with high dimensional data. And so how can we do this in CausalELM? So first, we're going to instantiate a model. So we just call double machine learning, and it needs to take at least 3 arguments, which will be x, t, and y, which are covariates, treatment, and outcomes. And there's a lot more keyword arguments that you can add in. If you are interested in seeing them, you can go look at the documentation. And once we've instantiated our model, we can just call estimate causal effects, or estimate causal effect, and we, in this case, we'll get back a scalar which represents, in this case, the average treatment effect, the effect of being eligible for 401k plans on net financial assets. And of course, you probably, after you've estimated your model, you want to get a summary of the model itself. And if you're coming from R, this probably looks familiar. You do this with like lm.summarize or something, and the same thing applies here. And you get this dictionary with a lot of different things that will make a little bit more sense later when I talk about what the ELM is in CausalELM, with like activation function, quantity of interest here. We can see we're estimating the ATE. And one thing to note here is that these standard error and p-value here are set to NaN. And if you don't want them to be NaN and you want to estimate them, you can use the keyword argument inference and set it to true. But the reason that it's set to NaN now is because it does take a while to run, because a lot of the models don't have like closed form confidence intervals. And so the way we estimate these non-parametric p-values and standard errors is through randomization inference, or permutation-based inference, and that takes a really long time. So by default, it's set to false. And so arguably the most important step in doing causal inference isn't estimating the effect, but it's actually validating your model, seeing how robust it is to violation of your modeling assumptions, or at least whether those assumptions that you're making are plausible. And so you can easily do some robustness checks in CausalELM just by calling the validate method. And so in this case, what you'll get back is a 3-tuple. You'll get a dictionary with the estimated causal effect under models that have simulated violations of the counterfactual consistency outcome. You'll get an E value, which represents how strong of an association there would need to be between a hidden confounder and the outcome to change your results, so kind of like getting after selection bias. And then the final thing you'll get is a matrix, which hopefully will be empty, and that matrix represents data points in your data set that have a predicted probability at or near 0 of being assigned to either treatment or control group. And so if you have an empty matrix here, that's good. That means you likely satisfy the positivity assumption. Okay, so we went through an example here of how we can estimate the expectation of tau I, this average treatment effect. But we might actually be more interested in individualized treatment effects, or conditional treatment effects, which we'll call the CATE here. So for example, we might be interested in estimating the effect of compensation to victims of violence in Afghan villages on future Taliban violence, not across the country as a whole, not an expectation, but maybe within individual villages, which vary a lot on things like ethnicity and language and geography. And so the data from this example that we're going to use comes from a recent study by Jason Lyle, who did just that using data from the U.S. Agency for International Development and event data from coalition forces in Afghanistan. And so again, a machine learning based approach is not the only way we could do this. What you could do, maybe if you want to look at heterogeneous treatment effects across, say, Pashtu versus non-Pashtu villages in Afghanistan, you could just subset those groups, estimate a linear regression for each of those groups. This would get really tedious really fast, especially like the more covariates you have, the more tedious this is going to get. And also in terms of statistical power, it's going to get really degraded really fast because you're going to be splitting the data up further and further, and you're going to be throwing away a lot of information. So it's really not ideal. But fortunately, we can use, among other things, a method called doubly robust estimation. And like double machine learning, we don't need to specify the functional form. And another benefit of doubly robust estimation too is that we specify multiple models here. And if we get the covariates correct for one of the two models, then we're going to have an unbiased estimate of the CATE. And so doubly robust estimation here uses, again, any ML models to predict treatments, predict outcomes conditional on the treatments, and then combines them into a final ML model to give you the CATE. And so once again, the workflow here is pretty much the same. We can instantiate a model, doubly robust learner here, pass in covariates, treatment, and outcome. And one thing to note here with these estimators is you can pass in either an array or arrays, or you can pass in any struct that implements the tables API, the tables interface. And so again, we call estimate causal effect, and here we get the CATE, and of course this is different than with estimating the ATE because these are individualized treatment effects, and so we get a vector of estimated treatment effects for each unit I, which in this case represents villages. And once again, we can get a summary of our model. It looks pretty similar to what we saw in the previous example, the one difference being the causal effect here is a vector rather than a scalar. And once again, by default, we don't have standard errors and p-values, but we can get them by setting the inference keyword argument to true. And again, we call validate. We can do those robustness checks. and make sure that our model is robust to at least small violations of our modeling assumptions, or see at least that it's plausible that the assumptions here, counterfactual consistency, no selection bias or no hidden confounding, and positivity are met. And so what you saw in those two examples, that is a general workflow for all of the estimators in CausalELM. So you instantiate a model depending on what type of estimation you want to do. You estimate causal effects using the estimate causal effect method. You can get a summary of your model using summarize, and you can also use the British spelling here if you prefer. And you would, of course, again, want to validate your modeling assumptions, which you can do with the validate method. And this applies across all of the models in CausalELM. And so we've been talking about, at least in the case of double machine learning and doubly robust estimation in CausalELM, they rely on some sort of machine learning model, right? And I didn't really specify what that was. I just said some machine learning model. But the ELM in CausalELM is that machine learning model. It's the base model that CausalELM relies on is an extreme learning machine. And the way an extreme learning machine works is it's a single layer neural network, but it does not use gradient descent. It actually uses randomized weights. And so what it does is it has this W matrix where the number of features correspond to the number of rows and the number of neurons are the number of columns. And those are all randomized. In this case, they come from a uniform distribution. Then we compute this hidden layer H by multiplying our inputs X by our weight matrix and applying G, which is an activation function on top of that hidden layer. And then now we have our output, our outcomes that we want to predict. And we have this nice matrix, and so we can easily get predictions by just solving the least squares problem. So we can get this vector beta by just multiplying y by the pseudo inverse of h. And then to make predictions here, we just pass in our test covariates, multiply them by our weights, apply our activation function on top of that, and then multiply by our learned parameters beta. And actually, in CausalELM, we don't just use one ELM, but we use an ensemble of ELMs. This is good because it reduces variance, and it also enables us to get probabilistic outputs, since each individual ELM is minimizing the least squares loss rather than, say, like cross entropy. You could, in theory, for an individual ELM have predictions a little bit outside of the range of discrete variables, but by using an ensemble, we can get probabilistic predictions. And in this case, by ensemble, we use a bagging strategy similar to like if you were to use random forests. And then as far as activation functions, there's 13 different activation functions, and we usually don't think about activation functions providing regularization. You usually think of like maybe dropout or L1 or L2, but actually, depending on what activation function you use, it can provide a degree of regularization to your model. More aggressive activation functions, like say the binary step function, are going to give you more regularization than a smoother function, like say swish. And this actually can greatly improve performance of your estimators here. So on that note, if you do run CausalELM and you get some estimate that looks pretty wonky, like you'll clearly be able to tell, don't panic. You're probably not wrong. Don't think you need to like run some cross-validation and do a bunch of fancy things. It's likely the case that you can just try a different activation function and you'll get good predictions. And so here I did mention, we went through a couple examples, but there's a bunch of different estimators here in CausalELM. So for computing average effects, you can do interrupted time series estimation, and from that you can compute mean effects or cumulative effects. There's G computation if you're familiar with the biostatistics literature, And with G computation, you can estimate both the average treatment effect or the average treatment effect of the treated, and of course, double machine learning, which we went over. And for CATE estimators, besides doubly robust estimation, which we just talked about, you can also do S learning, T learning, X learning, and R learning. And okay, so what is the design principles here of CausalELM, and how does it compare to other packages? So one of the big overarching things in CausalELM is simplicity. So when using CausalELM, there's no required imports. So if you've used something like econML in Python, or CausalLI, I think is Salesforce's maybe package in Python, they have a bunch of, you have to import other models. So they have these like classes that you can use as estimators, but for the machine learning models, you have to import like scikit-learn or stats models or something else, and then instantiate those models. That's not the case here. Another thing on that note is you only need to know really four functions: how to instantiate a model, estimate causal effect, summarize, and validate. And as far as inference goes, all of the models here use randomization inference, which is both a pro and a con. It takes a longer time to implement, but it's a pro in that like the p-values and the standard errors for all of the models all have the same interpretation. And one trade-off, of course, on that is that you do lose some flexibility. The estimator or the machine learning model here is based on extreme learning machines, so there's no like random forest or neural networks or anything else. So you do, in exchange for the simplicity, you lose a little bit of flexibility. It's also very interdisciplinary in its approach. So if you look at, again, a library like econML, most of the estimators implemented come from the literature on econometrics. In CausalELM, there's kind of a smorgasbord of different ideas here. So like G computation and this idea of the E value actually come from the epidemiology literature. A lot of these other estimators like doubleML, doubly robust estimation, come from econometrics or more broadly from statistics. And the idea of randomization comes broadly, randomization inference or permutation-based inference comes more broadly from the statistics literature. So there's no like single favored discipline or favored approach here in CausalELM. And then finally, it's designed to be hopefully very lightweight. So part of that is, of course, being written in Julia, which makes things pretty quick. And also, CausalELM is implemented entirely in the Julia standard library. So there are no dependencies other than for testing, we use the data frames package. Okay, so first off, I hope at least someone in the room has watched Step Brothers before and gets this reference. But what is the way forward for CausalELM, but more broadly, I think causal machine learning with Julia? So in CausalELM, we're thinking about implementing maybe more sort of estimators and implementing the in some cases implementing the instrumental variables version of some of these estimators like doubleML, doubly robust estimation, and adding support for using GPUs, which I think should not take too much time, to be honest. But more broadly, I think there is a case to be made for developing an ecosystem in Julia for doing causal machine learning. So sort of building an interface package, sort of like the geospatial community's done, or like tables.jl, so that if somebody reads a paper on a new method for causal machine learning, thinks it's cool, they want to implement it in Julia, they can do that, implement their algorithm, make sure they implement our interface, and then somebody as a user could use a simple interface similar to what CausalELM does, and if they just know these four functions, say how to instantiate the model, estimate the causal effect, summarize and validate their model, they can use pretty much any estimator that they want to know. And so, of course, always looking for contributions or feedback. So if anybody's interested, you can let me know after this talk, or I think the link to the repo or the docs is up here on the first slide too. So yeah, let me know. And that's the end of this presentation.
Thank you, Darren, Colby.
Thank you.
Thank you for enriching the Julia community. Has anybody from the audience thought of questions at the moment?
So first of all, thank you, because that's a package I wished we had a few years ago. How do you think about which estimator to choose on the average treatment effect side? What are kind of your defaults and how you think about it when you're choosing which one to kind of start with?
Man, that's a really good question. Well, I think it depends a little bit like on the structure of your data, right? So like if you have, say, time varying confounders, G computation might be your go-to. If you have a lot of covariates and you probably don't know how they're all going to fit in like the functional form, I'd say probably like a double ML. But in general, I think it's very problem specific. Like it depends on the question you're trying to answer, the data set you have, and then like the assumptions you're making, which as of now, we don't have instrumental variables based estimators implemented, but we might in the future, especially depending on demand. So that would of course come into play. And then of course, depending on what you're trying to estimate, and also whether your data is of a time series nature or not, and how many units you have. So if you have like a single unit that's treated at some point and it's like sort of a before and after thing, then by default you're going to use interrupted time series estimation. So hopefully that answers your question.
Well, thanks for your talk. It was really interesting and all your work. If I would need to use a different model other than the extreme learning machines, would it be simple to plug a different model and use all the rest of the machinery there?
I mean, it's open source, so in theory you could, but in practice, like I said, one of the principles here is simplicity, so you do lose flexibility, and so I don't want to like say you should use CausalELM in every possible scenario. So in that case, you might be better served by like econML in Python or something else. But that also gets to like what I just mentioned about maybe building out a general interface for CausalML so that someone like you who might be interested in using something else can have a single interface to estimate causal effects with whatever estimator you're interested in using.
Okay, thank you very much.
Let's give one more round of applause.